Welcome back to the deep dive. Today is Friday, February 20th, 2026.
Good to be here.
If you're listening to this in your car right now, maybe you're stuck in a bit of morning gridlock, I want you to do me a favor. Just look at the dashboard.
The screens have gotten massive, haven't they?
Oh, totally. Just look at that screen. Because today we're going to, well, metaphorically speaking, we're going to tear that dashboard apart.
Right down to the silicon.
Exactly. We want to look at the absolute wiring mess, the legal loopholes, and really the billion-dollar gambles that are happening right underneath your fingertips.
It's a completely different world under the hood than it was even 2 years ago. I mean, the shift is staggering.
It really is. And, to set the scene, we kind of have to rewind the clock a bit. Do you remember the Super Bowl ads from, say, 2021 or 2022?
Oh, the robotaxi revolution.
Right. The promise was that by February 2026, we wouldn't even be driving.
You'd be in the back of these steering wheel-free pods.
Yeah, sipping coffee, maybe playing cards, taking a nap.
The hype was just incredible.
Yeah. It was a technological fever. But looking at the window today, I still see a lot of steering wheels.
And a lot of stressed-out commuters.
Exactly. The fever for Level 4 and Level 5 fully autonomous driving has cooled off significantly. But, and this is really the core of our deep dive today, the industry didn't stop.
No, not at all. They just pivoted.
Right.
They got pragmatic. I mean, incredibly pragmatic. The industry collectively realized that trying to jump straight to a car that can drive anywhere, anytime without a human,
It's impossible.
it's like trying to build a colony on Mars before you've even figured out how to pitch a tent in your backyard.
So we've moved from hype to industrialization.
Exactly. We aren't trying to replace the driver immediately anymore. We're trying to augment the driver.
Augment them to a superhuman level.
Right, while simultaneously building the system resilience we actually need for the future.
So our mission today is to deconstruct this new reality. We're working off a stack of really dense material, specifically the 2024 to 2026 Global ADS Technology Strategy Report.
And the 6.1 ADS Strategic Analysis.
Yeah, which is heavy reading.
It is, but it's the absolute blueprint for the next decade of mobility.
We're going to break this down using a strict top-down MECE approach.
Mutually exclusive, collectively exhaustive.
Spoken like a true consultant.
Hey, sometimes the corporate jargon actually works. It keeps the analysis clean.
It keeps us honest, yeah. We're going to look at the business strategy, the regulatory gamesmanship, which honestly is fascinatingly cynical.
Very much so.
We'll look at the hardcore engineering under the hood, and finally, how they're testing these things without, killing anyone.
It's a story of how financial constraints and legal fears actually drove better innovation than all that early hype ever did.
Let's jump right into Section 1, the strategic bifurcation. Or, as I kind of like to call it, how car companies realized they were burning cash and decided to actually make money.
That is a very fair summary. The industry hit what we call the valley of death.
The valley of death, it sounds dramatic.
In venture capital terms, it's terrifying.
Break that down for us. Why a valley?
It's a fundamental cash flow problem. Developing a fully autonomous car, a true Level 4 vehicle with no driver, requires billions in R&D.
Right.
You need server farms, custom silicon, millions of miles of testing. But here's the kicker. The hardware to make that car safe is incredibly expensive.
How expensive are we talking?
We're talking over $5,000 just for the sensors and computers per car.
Wow. So you end up building a car that costs $100,000 or $200,000.
Exactly. And you cannot sell a $200,000 Honda Civic to a mass market consumer.
No one's buying that.
Right. So you have this massive R&D spend, but no product you can actually sell to regular people to recoup the investment. That gap where you spend billions but earn zero is the valley of death.
And companies that tried to jump straight across it.
They died. Or they were acquired for pennies on the dollar.
So they needed a bridge, a way to sell something today that pays for the research for tomorrow.
Precisely. And that necessity created the dual-track strategy that absolutely dominates the market today in 2026.
Two completely different business models running in parallel.
Yes. Let's unpack track 1.
This is the volume play, right? The report calls it Level 2 plus or supervised automation.
This is a car you likely own or are looking to buy today. The definition here is crucial, and it's a legal definition just as much as an engineering one.
Hands off, eyes on.
Exactly. Hands off, eyes on. You could take your hands off the wheel on the highway, maybe even in city traffic.
The car steers, it brakes, it changes lanes.
But you are still the captain of the ship.
I am legally responsible.
You are. And that legal distinction changes everything about the engineering. Because you are the backup, the car doesn't need to be mathematically perfect. It just needs to be very, very good.
Which brings the cost down.
Drastically. It allows the hardware cost to stay manageable. The ceiling for Track 1 is roughly under $2,000 per vehicle.
$2,000. That's the magic number.
For mass adoption, yes. For that price, you get urban and OA.
Navigate on autopilot.
Right. The car handles stop-and-go traffic, on-ramps, off-ramps. By this year, 2026, this isn't a luxury feature anymore.
No, it's standard on premium and mid-range vehicles. It's totally democratized.
But there's a psychological trick happening here, isn't there?
Yeah, I feel like there is, because drivers want the feeling of the future. They want the car to drive itself, but they don't want to pay the $5,000 price tag for all that extra redundancy.
That's exactly it. Consumers want the experience of autonomy. They want the stress relief of not micromanaging the brake pedal in a traffic jam.
Right.
They don't actually care if there's a backup steering motor in the trunk, as long as the system works 99% of the time.
Which brings us to Track 2, Level 3 and Level 4. The brand halo and the robotaxi.
This is the other side of the bifurcation. This is eyes off.
Where the car basically says, I have control. If we crash, it's the manufacturer's fault.
And once the manufacturer takes liability, the hardware equation flips completely.
Because now you need fail operational redundancy.
Drastically so. Once you take the human out of the loop legally, if the main computer dies, a backup computer must instantly take over.
If the steering motor fails, a backup motor kicks in.
You can't just beep and tell the driver to take the wheel if the power cuts out, because the driver might be reading a book.
Or sleeping.
Right. And that mechatronic redundancy is exactly why the cost jumps back over $5,000.
So that's why you only see true Level 3 flagship features in top-tier luxury models, like a Mercedes S-Class or a BMW 7 Series.
It's a technological totem.
Yeah.
It's there to show off engineering prowess. It is not there to generate volume sales. Not yet.
And then the extreme into Track 2 is the Level 4 robotaxi, your Waymo, your Cruise.
Correct. But they operate in strict geo-fenced areas, and the business model isn't selling cars to individuals.
It's mobility as a service. MaaS.
They are selling you a ride. Waymo is hitting 700,000 trips a week now, but that's a fleet service business. It's totally separate from the manufacturing business of selling cars to the public.
Okay, so we have the volume play with Level 2 plus funding the future, and the niche high-tech play with Level 3 and 4 establishing the brand.
That's the dual track.
But this leads us into Section 2. And honestly, this is where I get a little cynical reading the report, because when I read about their compliance strategy, it sounds less like engineering and more like a massive legal loophole.
It is certainly highly strategic. We call it downgrade to upgrade.
Downgrade to upgrade. Walk me through this.
Think about the hardware capabilities of a high-end L2++ car right now. It has 4K cameras, massive compute power, maybe LiDAR.
Technically, it physically could drive itself in most situations.
It is essentially an L3 vehicle in disguise.
But the manufacturer slaps an L2++ sticker on it.
Because the second they label it Level 3, they step right into the liability trap.
They have to deal with insurance.
They accept legal responsibility for accidents. And they have to navigate the certification nightmare of regulations, particularly UN R157.
UN R157. It sounds like a droid, but I assume it's a bureaucratic nightmare.
It is incredibly restrictive. Imagine having to fill out a tax return for every single micro decision the car makes.
Yikes.
UN R157 sets strict limits on what an L3 system can even attempt. Speed limits, lane change parameters, following distances. It strangles the user experience.
So if I'm a car CEO, I look at that and say, no thanks, I'll just call my system L2++ paint.
Exactly.
I'll give the customer 99% of the capability, urban NOA, mapeless driving, but because I call it L2, if they crash, it's their fault.
It is a strategic masterstroke. They downgrade the regulatory label to evade liability, but they upgrade the actual feature set to win over the consumer.
That is devilishly smart. Ruthless, but smart. But this strategy isn't uniform globally, is it?
Not at all.
The report highlights a massive regional strategic divergence. Europe, China, and North America are basically playing 3 different games.
Let's look at the drivers in each region. Europe is entirely regulation first.
The land of rules.
Everything is driven by the GSR, the General Safety Regulation, and Euro NCAP 2030.
So they care about safety above all else.
Specifically, Vulnerable Road User Protection, VRU. The innovation in Europe isn't focused on how cool it is to drive hands-free. It's focused on, does the car stop for a cyclist? Does it see the pedestrian stepping out from behind a delivery truck?
Okay, so Europe is the safety inspector. What about China?
China is the agile iteration market. It is moving at China's speed. The entire focus is on urban NOA and mapless navigation.
The consumer psychology there is totally different, isn't it? I read a stat in the source material that 55% of Chinese consumers would switch car brands just for better connectivity and ADS tech.
It's a staggering number. In the West, you might switch brands for reliability or styling. In China, if your car isn't smart, it is instantly obsolete.
Which forces Chinese OEMs to move incredibly fast.
They iterate software almost weekly.
Weekly updates for a car.
Yes. While a legacy Western automaker might push a major software update once a year, Chinese startups are pushing updates constantly. If you aren't mapless, meaning your car can navigate a complex city it has never seen before without a preloaded high-definition map, you are dead in the water.
And then there's North America.
North America is driven by compute power. And, let's be honest, litigation.
The Tesla influence.
Exactly. The safety floor is set by NHTSA mandates, like standard AEB, automatic emergency braking. But the ceiling is defined by who has the biggest computer chip and the best end-to-end AI model. It is a silicon arms race.
This brings us to what I think is the most fascinating concept in this entire section, the data flywheel.
The hidden economy of AD.
Right. We talked about L2++ being a revenue driver selling cars to make money, but the report suggests these cars are actually Trojan horses for data collection.
We call this shadow mode.
Shadow mode. How does that actually work in practice?
Imagine you buy a new 2026 vehicle. It has the latest hardware. You're driving to work, you're steering, you're braking, normal driving.
Sure.
But unbeknownst to you, running silently in the background on the car's computer is a newer, highly experimental version of the autonomous software.
But it's not controlling the wheels, right?
No. Absolutely not. That would be wildly dangerous. The experimental software is just shadowing you. It is making virtual decisions in real time.
So it's thinking, I would turn left here.
Exactly. It thinks I would brake now. And then, crucially, it compares its virtual decision to what you, the human driver, actually did in reality.
It's checking its homework against a human teacher.
Precisely. And this creates a quantitative oracle. The system is actively looking for deviations.
Give me an example of a deviation.
Let's say you swerve suddenly to avoid a pothole or a weird piece of debris on the highway that the AI didn't recognize as a threat. The system flags that moment.
It marks it as an edge case.
Right. It flags it as a high-entropy event.
Entropy?
Entropy measures uncertainty or confusion in the mathematical model. When the AI is confused or when the human does something the AI did not predict, that data is pure gold.
Because you can't program that stuff in a lab. You can't write a line of code for kid drops an ice cream cone in front of a unicycle.
You cannot replicate the chaos of the real world on a closed test track.
Yeah.
But if you have a million L2++ cars out on the public roads constantly watching for these high-entropy events.
You collect those rare edge cases at massive scale.
So the L2++ fleet pays for itself via retail sales. It avoids L3 liability because the driver is legally in charge, and it simultaneously generates the exact training data needed to build the true L4 models of the future.
It's a self-reinforcing loop. The more cars you sell, the more data you get. The more data you get, the better the AI becomes. The better the AI, the more cars you sell.
The definition of a flywheel.
That is incredibly efficient. And a little bit terrifying, which is usually the sign of a winning business strategy.
It's really the only pragmatic way to solve the long tail of driving scenarios.
All right, let's get our hands dirty here. We've covered the business strategy. Now I want to get under the hood. Section 3. Underlying technology and architecture evolution.
The hardware reality.
Because to make this shadow mode work, and to handle all this computation, the car itself had to change physically.
A fundamental shift. We are seeing the industry finalize the move to zonal architecture.
Explain the problem with the old way. Why couldn't we just use the existing wiring in the cars?
If you look at the wiring harness,
Yeah.
the nervous system of a car from 2010 or even 2018, it was chaotic. It was based on the CAN bus system.
Right.
Imagine a long single wire running the length of the car. And every component, the window switch, the door lock, the engine sensor, was just clipped onto it, shouting short messages back and forth.
Like a crowded room where everyone is just yelling over each other.
Exactly. And that worked perfectly fine for rolling down windows or locking doors. But now, try to push uncompressed 4K video from 6 different cameras, plus point clouds from a LiDAR, plus 4D radar data, all through that same wire.
It chokes.
It instantly bottlenecks. It's like trying to drink from a fire hose with a coffee stirrer. The bandwidth simply isn't there.
So the fix is zonal architecture,
Think of it as decentralizing the car's nervous system. The vehicle is divided into physical zones.
like front left, rear right.
Yes. You have zone control units, or ZCUs, in the corners. These are mini brains. The front left ZCU gathers all the massive data from that specific corner: the headlight matrix, the wheel speed sensor, the corner radar.
It packages it all up locally.
It packages it and then sends it over a super high-speed Ethernet backbone straight to the central compute platform,
The CCP, the big brain.
the big brain,
Mm-hmm.
like the NVIDIA Thor or the Snapdragon Ride Elite. And this connection isn't just standard internet wiring. It utilizes TSN, time-sensitive networking.
I saw that acronym in the report. Why is time sensitive so critical here?
Synchronization. This is absolutely vital for AI perception. Imagine you were driving at 100 kilometers an hour.
Okay.
Your front camera takes a frame, and your LiDAR sweeps the road. If those two pieces of data arrive at the central compute platform even a few milliseconds apart, the car's understanding of reality gets distorted.
Because the car moved in those few milliseconds.
Exactly. The camera data says the pedestrian is here, but the LiDAR data, which arrived 3 milliseconds later, says they are over there.
It causes smearing.
It causes massive disorientation for the AI. It's like watching a movie where the audio is out of sync with the video. But instead of just being an annoying movie, it causes a high-speed collision.
Wow. So TSN fixes that.
TSN ensures that every single packet of data is time-stamped with microsecond precision. It guarantees the central brain sees a perfectly coherent, synchronized reality.
Microsecond precision. That is wild. But to run these central brains, these tiny 5 nanometer and 7 nanometer superchips, you need incredibly clean power.
Yes, power integrity.
The report mentions this as a hidden hero. And this seems like a tiny detail most people would skip over, but you flagged it as essential.
It is the bedrock of system stability. Modern AI chips operate at very low voltages, usually around 0.6 volts.
That's tiny.
It is,
Wow.
but their current consumption swings wildly. When the neural network suddenly engages to process a complex, chaotic intersection, the current draw spikes instantly. We're talking spikes of tens of amps in a matter of nanoseconds.
And if the car's power supply can't keep up with that spike?
The voltage drops. If it drops even a tiny bit, say from 0.6 volts down to 0.55 volts, the processor can physically glitch.
A bit flips.
A bit flips. The AI hallucinates or reboots. In a laptop, you get a blue screen of death.
In a car moving at highway speeds.
You get a real death. So the engineering solution involves specialized components. The report specifically highlights Murata's 3-terminal low ESL capacitors.
ESL. What does that stand for?
Equivalent series inductance. Think of inductance as resistance to sudden change. Standard capacitors are too slow to release their stored energy when the chip demands it instantly.
They're a bottleneck.
Exactly. These specialized Murata caps are like sprinters. They can discharge energy incredibly fast to fill that gap during a massive current spike.
So they replace the standard ones.
Often, one specialized Murata capacitor can do the job of 6 standard ones. It entirely stabilizes the heartbeat of the ADS processor, so it never skips a beat no matter how hard the AI is thinking.
That is the kind of hardware detail that makes this deep dive worthwhile. It's not just software code, it's physical capacitors keeping us alive.
Hardware is hard.
Speaking of code, though, the brain itself is changing. We are moving from a modular approach to end-to-end.
The algorithmic paradigm shift. This is huge.
Explain the old way first.
The old modular stack was like a factory assembly line. You had a perception module. Its only job was to look at pixels and say, I see a car.
Okay.
It passed that text label to the prediction module, which calculated the car's moving left. Then that goes to the planning module, which decides I should slow down. And finally to the control module to hit the brakes.
Perception, prediction, planning, control, step by step by step.
The problem is, at every handoff, you lose information.
Right.
It's a game of telephone. By the time the signal gets to the control module, all the rich nuance of the actual visual scene is lost.
So the new way, the 2026 way, is end-to-end, E2E.
Exactly. Raw sensor data video, radar, LiDAR goes into one side of a massive neural network, and a driving trajectory steering angle, brake pressure, comes out the other side.
No middleman.
No middleman. The AI learns the implicit rules of driving by observing human data, not by being programmed with rigid if-then statements by an engineer.
They're using BEV and transformers for this, right? Bird's eye view.
Yes. Taking 2D camera images from all around the car and mathematically transforming them into a 3D top-down vector space.
And occupancy networks. I love this concept in the report.
It's brilliant. Instead of trying to teach the AI to identify every object in the world, this is a dog, this is a stop sign, this is a plastic bag, This system uses voxels, 3D pixels.
It just asks, is this piece of space occupied?
Right. It identifies that a voxel is occupied by matter. It doesn't care what the matter is. This solves the GOD problem.
General obstacle detection.
Yes. If a truck overturns and spills a weirdly shaped industrial machine onto the highway, the old AI might not recognize it because it wasn't in its training library. It might just crash into it.
But the occupancy network just says, hey, there's a big chunk of matter right there. Don't drive into it.
Exactly. It's an elegant solution to the unknown. And they are combining this with VLA models now. Vision language action.
Introducing common sense.
Right. Understanding context.
Right.
Not just detecting a human shape, but understanding that it's a police officer making a specific hand gesture to stop. Or understanding a complex handwritten construction sign.
Which is incredible.
Yeah.
Now, I want to pivot to a specific hardware evolution mentioned in the report because it solves a very scary real-world problem. Ghost braking.
Ah, yes. The Westerschelde Tunnel case study. This is a classic example of engineering theory crashing into reality.
For those who don't know the story, tell us what happened in the Netherlands, because this reads like a true crime story for automotive engineers.
It really does. Drivers in the Westerschelde Tunnel were experiencing terrifying phantom braking events.
Just out of nowhere.
Out of nowhere. They would be driving along in the tunnel at 100 kilometers an hour, and suddenly the car's ADS system would slam on the brakes, hard, for absolutely no apparent reason.
Which is incredibly dangerous, especially in a tunnel where there's nowhere to swerve and cars are right behind you.
Extremely dangerous. The root cause was the traditional radar sensors. They were what we call 2+1D radars.
2+1D.
They flattened the world. They could tell exactly how far away a metal object was, and they knew roughly where it was left to right, azimuth.
Okay.
But they were terrible at elevation. They couldn't see up and down accurately.
So the radar sees a massive chunk of metal ahead. It knows it's exactly 50 meters away, but it doesn't know if it's sitting on the asphalt or hanging above the asphalt.
Exactly. And in this specific tunnel, there were large, heavy metal ventilation fans hanging from the ceiling.
Oh, wow.
To the 2+1D radar, a massive metal fan hanging on the ceiling looked mathematically identical to a stopped car blocking the road at that specific distance.
Because it flattened the 3D world into a 2D pancake.
Correct. And the multipath effect, the radar waves bouncing wildly off the curved tunnel walls, made the signal even noisier. The car's computer had to make a split-second guess. Is that a car or a fan?
And for safety, it defaults to braking.
It guesses car and slams the brakes.
Yeah.
Phantom braking.
So how did the industry fix this?
The fix, which is scaling massively now in 2026, is 4D imaging radar.
The fourth dimension being elevation?
Yes, true height. These new radars use MIMO technology, multiple input, multiple output. They have over 2,000 virtual channels.
So it's much higher resolution.
It creates a dense point cloud almost rivaling LiDAR. Now, the radar can clearly see the z-axis. It says that big metal object is 4 meters off the ground. It's a fan. Ignore it. That other metal object is on the ground. It's a car. Brake.
It adds the z-axis back to the world.
Finally solving the ghost braking issue in complex vertical environments. It is a massive leap forward for system reliability.
Okay, so we have the zonal tech, the end-to-end AI, the 4D radar, but we have a massive problem. The report calls it the data tsunami.
It is an overwhelming logistical nightmare. A single L3 test car generates about 500 terabytes of data per day.
500 terabytes every single day per car. That's insane. You can't just upload that to the cloud over 5G.
It's physically impossible. You would need a dedicated fiber optic line plugged into the car while it's driving.
Yeah.
If you have a fleet of 10,000 cars, you are generating more data than the entire internet can reasonably handle.
So the industry had to figure out how to throw most of it away.
They moved to smart logging.
This is where companies like Electrobit come in, right?
Yes. They deploy edge intelligence. The filtering software sits directly on the car itself and processes the data in real time. It uses trigger logic.
So it's not just hitting record and saving everything. It's waiting for something interesting to happen.
Exactly. It completely deletes the 99% of boring highway driving where nothing happens. The AI only saves data when specific conditions are met.
Like what?
1, if the automatic emergency braking is triggered. 2, if the AI reaches that state of high uncertainty or high entropy we talked about.
When it gets confused.
Right. Or 3, if there is a stark discrepancy between the high-definition map and the visual reality, like a traffic sign that was changed yesterday.
So it throws away the hay and only keeps the needles.
It reduces the data storage and transmission needs by 90 to 100 times. It turns a paralyzing tsunami into a manageable, highly curated stream of high-value insight.
And this feeds perfectly into Section 4, the validation revolution. Because even with all this data, we can't test these cars just by driving them around the block a billion times.
We call that brute force testing, and it simply doesn't scale. It takes way too long, and it burns too much capital. The industry has shifted 80% of its validation to the virtual world.
Software in the loop. Silo.
And the zero prototypes vision. Companies like VI Grade are building hyper-realistic digital twins. They allow engineers to test millions of edge case scenarios using supercomputers before a physical car is ever built.
They can simulate rain, snow, blinding sun, a child running out from between parked cars, millions of times overnight.
Exactly. But you do still need some physical testing, especially for the regulators.
Right. Euro NCKP isn't going to just take your word for it based on a video game simulation.
They demand physical proof. But the physical testing has gotten remarkably sophisticated. We are seeing a new generation of soft targets.
I looked this up after reading the report. The Soft Bicycle 360 from AB Dynamics. I watched a video of it. It is fascinating.
It's a brilliant piece of engineering.
But to the naked eye, it just looks like a block of foam cut into the shape of a person on a bike.
It does, but it's incredibly high-tech. It is crucial for passing the Euro NCKP 2030 standards. The key feature of this dummy isn't its shape. It's that it has articulating spinning wheels.
Why do the wheels need to articulate if it's just a dummy on a sled?
Because of the microdoppler effect.
Okay, break that down.
Radar works by detecting frequency shifts based on motion, the Doppler effect. It doesn't just see a static chunk of metal, it sees the velocity. Now, a real bicycle moving forward have wheels that are spinning.
Right.
That rotational spinning creates a very specific secondary radar signature, a microdoppler shift, that is distinct from the forward motion of the bike itself.
Oh, I see. So if the dummy bike just slides along a track without spinning its wheels?
The car's 4D radar looks at it and says, that's fake. Real bikes have spinning wheels. This object doesn't.
So the AI classifies it as a static glitch or non-threat and ignores it.
And fails the test. To validate the system properly, the dummy must have wheels that spin at the exact proportional speed to its forward motion to perfectly mimic the microdoppler signature of a real cyclist.
That is absurdly precise. And what happens if the car fails the test and hits the dummy at 60 kilometers an hour?
It explodes into pieces of soft, harmless foam. You protect the million-dollar prototype vehicle from damage, and you can reassemble the bike dummy in minutes for the next test run.
Rapid reset. That is testing efficiency at its absolute finest. Okay, we're heading into the home stretch here. Let's talk about the market reality. Section 5, market penetration and democratization.
The big headline here is that high-end ADAS tech is trickling down faster than anyone predicted.
L2++ is no longer just for $100,000 luxury cruisers.
Not at all. We are seeing full NOA capabilities moving aggressively into sub-200,000 RMB vehicles.
Which is roughly 30,000 US dollars. That is the mass market price point.
That's where the volume is. By 2030, the projections say that vehicles with level 2 or higher will account for 52% of global new car sales.
That's a tipping point. More than half of all new cars sold will have advanced autonomy.
It is becoming the baseline expectation for the modern consumer, much like Bluetooth or air conditioning was in previous decades. If a new car doesn't have it, it feels fundamentally broken to the buyer.
And powering this baseline is a fierce, massive battle between two silicon giants, NVIDIA and Qualcomm.
The clash of the titans in automotive compute.
On one side, you have NVIDIA with the Thor chip.
Thor is the absolute powerhouse. It boasts 2,000 TOPS, trillions of operations per second.
The brute force approach.
It is designed for the highest end, the robotaxis, the L3 flagships. It's for when you need absolute maximum AI compute, and power draw is a secondary concern.
And on the other side, Qualcomm with the Snapdragon Ride Elite.
Qualcomm is playing the efficiency card. Remember, their DNA is in the mobile phone world. They know how to squeeze every drop of performance out of a constrained battery. Their chip offers vastly superior performance per watt.
Which is crucial for EVs, right? Because of range anxiety.
It's a critical metric. In an electric vehicle, every single watt you burn on the computer is a watt you cannot use to drive the physical wheels.
So a power-hungry chip literally shrinks your driving range.
Exactly. If your supercomputer drains the battery, your range drops by 10 or 20 miles. Qualcomm is arguing that you don't need a nuclear reactor in your trunk. You need a highly efficient brain so you don't kill your mileage.
And Mobileye, are they still a factor in 2026?
Absolutely. Mobileye is still a major player. They are focusing heavily on cost-effective vision-first solutions like the IQ6. They're the masters of doing a whole lot with a little.
Which appeals to the mass market OEMs who are counting every single penny to keep that retail car price under $30,000.
Exactly. It's a three-way race with very different philosophies.
So let's wrap this up. We've gone from the chaotic, wild hype of cars without steering wheels to this incredibly sophisticated, highly industrialized machine.
It's a maturity story. We stopped trying to sprint to the moon and just started building a really, really good airplane.
Let's synthesize this. We moved from tech hype to pragmatic engineering.
We stopped trying to replace the driver immediately and started augmenting the driver to fund the future research.
And the car itself changed fundamentally. It's not just a mechanical machine anymore.
No, it is a physical AI agent. It perceives the world, it thinks, it learns, it communicates with the cloud, and most importantly, it learns from every single mile driven.
Which brings me to our final provocative thought for today, and this one. This one might actually keep you up at night.
Let's hear it.
We talked about shadow mode, we talked about the day of flywheel, millions of L2++ cars out there right now collecting data on human driving to train the L4 systems of the future.
Yes, that is the core data strategy of the entire industry.
So let's be totally real for a second. If I buy a $30,000 L2++ car and I drive it to work every day, correcting its minor mistakes, feeding it edge cases, teaching it how to navigate a messy construction zone, am I effectively an unpaid laborer?
That is a profound way to look at it.
I mean, think about it. I am paying the car company $30,000 for the privilege of training their robot to eventually replace me.
You are. You are the quality assurance engineer, and you are paying them for the job. You are generating the intellectual property that will eventually make the steering wheel obsolete.
And here's the second part of that thought. At what point does the shadow mode become so good because of all our collective training data that not letting the AI drive becomes the liability?
That is the singularity moment for the insurance industry.
The tipping point.
The exact moment the data proves definitively that the shadow mode is statistically safer than you are, that it crashes 10 times less often than a human being. Your insurance premiums for manual driving might just skyrocket.
A human driver tax.
Exactly. Because at that point, you are the unpredictable variable. You are the risk. The machine is the safe bet. It won't be illegal to drive yourself. It will just be financially irresponsible.
Well, on that cheery note, next time you're in gridlock, take a look at your dashboard again. It's not just plastic and glass and a navigation screen. It's a massive data collector. It's a student, and it is watching you learn so it can eventually take your job.
Until next time, keep analyzing.
Thanks for listening to The Deep Dive.